Okay. Hello, everyone, and welcome to the lecture. Can you please confirm if you can see my screen and hear me clearly? Okay, thank you. So today we have first student presentation, and I think the name of student is Ezra, right? Uh, Let me check if the student is here or not. Yeah, Ezra, you are presenting today, right? Can you hear me?
I thought I was presenter too.
Sorry, you thought you were presenting what? Are you?
I don't think it's me. I think it's Caleb Frank.
Oh, okay. Let me check. I asked this because you were sending me email. Let me check the schedule quickly. Yeah, it's Celeb Frank. Okay, Celeb, are you in the class?
Yes, I'm here.
Okay, so can you send me your slides by email? And I will let you share your screen, but just as a, backup plan, can you send me your screen, your slides through the email?
Sure.
Okay, thank you. So I will give you the time at towards the end of the lecture, but let me use this initial 30 to 40 minutes. Uh, okay, so uh, okay, so a student is asking that is the presentation, they are supposed to present the whole paper or just the sections? It is mentioned here, right? So, for example, Celeb, he will be presenting section 5.1 to 5.4, Ezra 5.5 to 5.6, and for example, the student Nicholas, presenter 5, will be presenting the whole paper, not only section, whole paper, paper 2. Okay. So, okay, now let me get back to the slides. So last time we were talking about privilege level switching, right? And we said why we need this privilege level switching when there are some situations when ring 3 code needs to transfer the control to ring 0 code, ring 0 level code, or ring 0 level code needs to transfer the execution control back to the ring 3 level code, right? Mm, no, I haven't posted it. I will post it after the uh, so actually these were the slides for Tuesday. Okay, so let me do this like this. I can let me not cover these slides now. I can cover them in a video later on, and let me then cover the slides which I prepared for today. Okay, so I am skipping that part. I'm directly moving to the part where we are going to talk about out of order execution, right? So it is basically section 2.10. I know I'm running much behind the schedule, but I'm fine with that because I want you to cover, I want to use this time to cover the material without, rushing as much as I can. Okay. So, uh, these slides, which I am going to share with you here, I haven't prepared them. These are the slides borrowed from Professor Onur Mutlu of ETS Zurich. Okay, so what is in order and out of order execution? In order execution is like basically there are two notions. One is program order and one is the execution order. Program order is the order in which you have written your program or your code, right? So normally we expect that the instructions in the order which they are written, they are executed in this by the processor or the hardware in the same order. So if they are executed in the same order, so we say the program order is same as the execution order, right? Our execution order is same as the program order. However, if the order in which the instructions are written is different from the order, the order in which instructions are executed is different than the order in which they are written in the program, then we say that the instructions are executed out of order, right? So here we are first going to talk about in order execution, and then I will explain what is out of order. Okay. So here we are looking at a here we are looking at a pipeline processor, and it has four stages. actually 5 stages: fetch, decode, execute, right? E stands for execute, and R stands for write to reorder buffer. I will explain what is reorder buffer. And this W stands for write back to registers or the memory. So this R stands for write to reorder buffer. And so R is for reorder buffer. And this W stands for write operation, write to register file or write to the memory, right? Now you can ask, okay, why the execution stage is like different for different kind of operation. For example, for integer add, we are saying one stage, and then for integer multiply, we are saying 4 stages, and then for floating point multiply, we are saying like 7 stages. This is because uh, integer operation, if you're adding in integer numbers, then it will be completed in one cycle. And if you are doing the multiplication, integer multiplication, we are assuming it gets completed in 4 cycles. So we have 4 stages. And for similarly, for floating point multiplication, it takes even longer. So that's why we are saying it takes, let's say, 7 cycles. So we have 7 stages. Okay. Now, what is the decode? Fetch is basically simply bringing the instruction or reading the instruction from the memory and bringing it into the core. So you put it in the instruction register, right? Decode stage is when you access the register file or the reorder buffer. For now, for time being, don't worry about what is reorder buffer. So reorder buffer is just a place to hold the data, just like register file is a place to hold the data. Okay. So it depends where the data is. So depending upon that, in decode stage, you access register file or the reorder buffer, wherever you find the required data. And also, you allocate the instruction which you are decoding. For it, you allocate an entry in reorder buffer. Actually, we will have an example or simulation, so it will become clear to you. Okay. So, and then you check if the instruction can execute or not, right? So, which basically mean that all the data which the instruction needs, all the operands, are they available? If they are available, so then you dispatch the instruction. Okay. Dispatch the instruction for execution. And what you do in this execute stage? The instruction is executed uh, out of order. So these are the like this is the pipeline, and here in this pipeline, what we are assuming is that dispatch and execution, these two steps are performed always in order. In order mean in the instructions are dispatched and executed. Sorry, instructions are dispatched in the same order as the program order. However, instructions are uh, executed and complete their execution out of order. So the order in which they execute and the order in which they complete their execution is different from the program order. Okay. So execute stages when you are doing the execution of the instruction. Complete stages when you write the result to reorder buffer. Okay. And write a retirement stage or commit stage, which is indicated by W. It is when you basically write the result produced by an instruction into the destination, and that destination can be a register, or that destination can be memory. Okay. So what we do is that we check the oldest instruction where in the reorder buffer, and we check the oldest instruction, and if it has no issues or no problems, then we allow it to commit, which means we allow it to write its result into the register file, all the memory. Okay. Okay, now before we go deeper about out of order execution, let's first focus on, let me explain some type of data dependencies. There are 3 types of data dependencies: read after write, data dependencies between what? Between instructions in a program. Read after write, write after read, and write after write. So here are the examples. So if you have first instruction and it is producing the data in the R3, and there is another instruction in the instruction order in the program, which is younger. Younger mean that it comes after the first instruction. And this younger instruction is reading the data from register R3, which was produced by the earlier instruction. So it's mean that there is read after write dependency. Why? Because second instruction can read R3 only after it has been written by the first instruction. Okay. I know I am going a little bit fast, but stop me. And also, please ask questions. Okay. And And also, if so your fellow students ask the question, try to answer them. Okay. So the second kind of dependency is right after read dependency. So for example, here in the first instruction, R1 is a source register, right? But in the second instruction, R1 is a destination register. However, the second instruction can write the result in R1 only after first instruction has read the data from R1. Why? Because if we allow second instruction to write the result before first instruction reads the result from R1, then it will overwrite the content of R1 and first instruction will get the corrupted input, right? So this is called write after read. So second instruction must write after the first instruction has read the data from the register. And third kind of dependency is write after read, where two instructions, they are writing the data to the they are producing the data into the same register, right? Like first instruction is producing in R3, second is also producing in the R3. So the second instruction can write the data in R3 only after the first instruction has written its output in the R3. So this is known as write after write or var dependency. Is everyone clear on this? Any question on this slide? I know it is not covered in the lecture, in the paper. That's why I didn't ask you to post your questions before starting the slide. So any questions now about these dependencies? If no questions, please say no questions so that I can quickly move on. Write after write, so the same written output is used twice. No, same, it is not like the same output is used twice. It is like same destination or same register is used twice. So, but at different time, it is supposed to hold two different results. Okay. Now, out of these, only Ra is a real dependency. Why we say that Ra is a real dependency? Because we cannot resolve the Ra. Other than that, var and var, they are not real dependencies because we can easily resolve them. So let me give you an example with the easiest one. So how can I resolve var dependency between these two instructions? Simply by using, let's say, R4. Here I say, I rewrite the instruction, I say, don't use R3, use R4, right? So it's not, I can it will not affect correctness of my program or my code, right? Now so it is resolved only by using a different register or renaming the register. Uh, I can also resolve right after read dependency by simply using the renaming, right? So for example, there is no real dependency between first and second instruction here. I can simply say here, don't use R1 here, use R6, right? So if I do that, it will not affect correctness of my program. However, I cannot resolve the raw dependency by using a different register, right? Because there is a real dependency. So second instruction uses the output produced by the first instruction as an input, right? So this dependency is not becoming because of the content holder, but it is becoming because of the actual content, right? So that is why this is real dependency, and we cannot resolve it by simply renaming. Okay, renaming the registers. Okay. So why I explained this? Because when we will be doing the when we'll be looking at out of order execution, then raw dependency is one which is like creates the problem in achieving the out of order dependency, out of order execution. Okay. Okay. So again, we are looking at this in order pipeline here, right? So dispatch is what? Dispatch is act of sending an instruction to a functional unit. So here you are fetching the instruction, and then in decode stage, you are decoding like what type of instruction is it? Is it an integer multiply? Is it integer add? Is it floating multiply or what? And depending upon the type of the instruction, you will either send it to the integer adder, integer multiplier, floating point multiplier, and so on, right? So this act of sending an instruction to functional unit is known as dispatching an instruction, right? Now, ROB, a reorder buffer, it gives us a mechanism through which we can rename through which we can actually achieve the renaming of the register. Here I gave you a very quick example of like I can replace R3 with R4 or R1 with R6, and I will then get rid of var and var. But how it is actually implemented, this is like human level understanding. But in machine, in hardware, how we implement it, by using the reorder buffer. So the reorder buffer gives us a mechanism to get rid of those dependencies, and as a result, uh, there are no stalls, or we don't end up wasting cycles because of those false dependencies. However, read-only buffer, it cannot resolve the real dependency, which is read after write. Okay, so it must respect it, and it is not resolvable. It must be respected. Okay, so the issue is that if you have a non-ready instruction stars the dispatch of younger instruction into the functional units, right? So now, for example, if you have for example, let's say you have this code, and the reorder buffer allow you a mechanism to rename these registers. Now, what you can do is that you can even execute this instruction before the first instruction, right? You can change the order, no issue, right? Same here. If reorder buffer allows you to do the renaming, you can move this. If you see that there is an advantage in doing so, then you can move this instruction or execute this instruction before the first instruction, right? However, uh, the the problem with this one is that you cannot move it uh, before the first instruction. Why? Because it actually is waiting for the content to become available, this content here, right? So if this result is not available, this instruction is not done. Let's say the first instruction takes 100 cycles to complete, right? And the second instruction takes 1 cycle to complete, right? So the second instruction will wait for 100 cycles for the first instruction to complete, and only then it can be executed, right? Which means that the wait or latency seen by the second instruction will be 101 cycles, not 1 cycle, 101 cycles, right? So the problem is that if the first instruction is not ready, it will stall the dispatch of the younger instructions into the functional execution units, right? So here is just like everyday life example of like how a non-ready instruction stalls the pipeline. So if you have uh, a long latency instruction which is like taking longer and it is not yet ready to leave the pipeline, then it will stall the pipeline for all other instructions which are waiting behind it, in the which are waiting under it or behind it in your program order, right? So they cannot execute. So then if we use the out of order, if we somehow we say, okay, this instruction does not depend upon this long instruction, there is no dependency, and we can allow this instruction to go ahead and execute, right? Yeah, we can do that. But if there is real dependency between this instruction and the long instruction shown in the red, then if there is real dependency, we cannot move it ahead of the long instruction because there is real dependency. For example, let's say there are some passengers who must get off from this train and move into this train, and then this train can only continue, right? So it's mean that this train must first stop, allow the passengers to get off, and then get on board on the train behind it, and then only the train behind the first one can continue its travel. Okay, so can we do better can we do better? Basically it's mean that can we speed up the execution, can we allow the younger instruction to go ahead and execute out of order? Okay, so what do the following two pieces of code have in common, right? So the common thing is that add instruction in both cases, first add, it will stall the whole pipeline. Why it will stall the whole pipeline? Because see that the first instruction is producing R3, right? And that R3 is used as a source in the second add, right? Now remember that multiply is more expensive. Let's say it takes 6 cycles, right? So after 6 cycles, the R3 will get the product, and that product will then be used by the next add instruction. However, the second add instruction is not dependent upon the mul. But the issue is that since we are doing the in order execution here, so third instruction can be executed only after the second instruction, and second instruction can be executed only after the first instruction, right? Same is true in this code here, right? So first add stalls the whole pipeline. Add cannot dispatch because its source registers are unavailable. R3 is unavailable. R3 is unavailable until the load instruction is done here, or multiply instruction is done in this code snippet, right? So later independent instructions cannot get dispatched. These instructions which are independent, like third instruction here and fourth instruction here, they cannot get dispatched because they are blocked by the instructions order in the program order. And when I say block, because they are taking longer. Longer mean that, for example, multiply, let's say, takes 6 cycles, add then takes 4 cycles, and here let's say load takes 100 cycles, right? So now these will be blocked even for longer time as compared to this code example. Okay, I think there is some question. Are these optimizations similar to how the C compiler works when optimizing instruction order? Okay, let me finish this slide and then I will take the questions. Okay, so later independent instructions, they cannot get dispatched, right? How are the above code portions different? The above code portions are different in the sense that the second instruction here is the first instruction here is multiply, and here the first instruction is load. So we know that typically the latency of multiply instruction is fixed. Let's say 6 cycles in a processor. However, the latency, how long it takes to complete the load instruction, it is not fixed, it is variable. Why it is variable? Because it depends that the data you are because loading the data from the memory, and it depends where is that data located. If it is in cache L1 cache, it will take less time. If it is in L2 cache, it will take longer. If it is in L3 cache, it will take even longer. If it is in memory, it will take super long. Okay, so that's why it depends where the data is, and depending upon that, latency is variable. Okay, now let me take the questions. Are these optimizations similar to how the C compiler works when optimizing instruction order and renaming? Actually, the C compiler, yes, it can do something like to improve the performance. For example, as you said, instruction ordering and renaming, but it cannot even if the compiler has even done the instruction ordering and renaming, hardware is necessary, but the hardware needed for doing out of order execution is necessary. But the other thing is that the basic concept is same. The instruction reordering done in compiler, the philosophy behind doing that instruction reordering, and philosophy behind out of order execution is same, which is basically to allow the independent instructions to go ahead and execute earlier. Is out of order execution implemented in the CPU or software? It is implemented in your hardware, the pipeline. Okay. I think your one student answer. Okay. Is out of order execution more prone to errors, exception, or is it the same as sequential execution? If you have designed your out of order algorithm correctly, then it is not the question of whether it is more prone to error or not, because it depends upon your design and your algorithm. However, definitely it is more complex as compared to in order execution. It makes your hardware, your pipeline more convoluted and more expensive, both in terms of complexity and space or amount of hardware. How does Intel SGX prevent out of order execution from exposing enclave data? We will hopefully look at it later in later part of the paper, but for the time being, we want to only focus on the background part of the paper. Okay, now let me go to the next slide. Okay, so one student asked, why are dispatch stalls bad? Anyone who want to answer this question, go ahead, unmute yourself and respond.
So it makes the computation slower because it has to wait for the one with the long dependency to execute before it can execute all the others.
Yeah, all the
So
younger instructions in the program, they need to wait for the older instruction to complete. And if the older one is taking long, the younger one cannot be dispatched. So which means that your, for example, if you have, let's say you have fetch, you have decode, and then here you have the execute stages. If the execute stage is taking 6 stalls, right? And now the and there is another multiply instruction. So fetch and decode, it is fetched, it is decoded, but it cannot enter into the multiplier because multiplier stage is occupied, right? Or if even if the second instruction is not multiply, but it is a add instruction or some other instruction which depends upon the older instruction and its result is not ready, then the younger instruction cannot be dispatched. Or even more simpler case, if we are saying in order execution. So in order is like we can allow the younger instructions only when the older one is completed. If the older one is not, even when there is no dependency, because since we are following the strict program order, so older can execute, younger can execute only when older is completed. So if older is taking longer, younger will have to wait. And it will be actually wasting of the resources. Okay, now let me go to the next slide. So what is the problem? Problem is in order dispatch, right? So because we went, as I said, if we are saying that as long as the older is not completed, we'll not allow the younger. So if the older is taking too long, just like in our example, if there is a long train, right? And it is taking long for the long train to go through the station or through the how to platform to empty the platform, it takes long. So it's mean the trains behind it, they cannot enter in the station or the platform, right? So this is the problem. So in order dispatch is basically a problem. Even when younger, maybe even when the younger instructions are ready, but we are since following a strict program order, we cannot allow the younger instructions to execute, right? So what is the solution? The solution is out of order dispatch, which is basically means that if we find a younger instruction which has no dependencies on the older instruction, which means it is ready to execute, so we should allow it to break the order and go ahead and execute out of order. Okay. So the basic idea is that we fire an instruction only when its inputs are ready. So if an instruction reads register R1 and R2 and the inputs of R1 and R2 are not dependent upon on older instruction, we should allow that younger instruction to go ahead and execute. So the idea is that we move the non-ready instructions out of the way of independent ones. We are not saying that we block them or we pause them. We still allow them to continue their execution, but we simply devise a mechanism in such a way that they do not block the way of the younger independent instructions, such that such that the independent ones can dispatch. So it is just like we create the rest areas for non-ready instructions and we put them in the reservation stations. So if you have an older instruction, let's say 1, and you have a younger instruction 2, now there can be two situations. 2 has a real dependency on 1. If 2 has a real dependency on 1, then it cannot execute, right? So what we will do is, okay, we will put the 2 to the reservation station or a rest area. Let me use the name as a reservation station, right? And let's say after 2 we have a instruction 3 which has no dependency on 2 and no dependency on 1. We can allow 3 to go ahead and execute. So we can allow it to go and execute. Okay. And 2 will keep waiting in the resting area as long as its inputs are not ready. Once its input are ready, we will take it out of the reservation station and allow it to go ahead and execute. Okay. So we'll keep monitoring the source value of each instruction in the resting area. And when all of the source values of instructions are available, we will fire that instruction or will dispatch that instruction for execution. So instruction dispatched. Okay, this is not important. I am just skipping this bullet point. Okay. So what is the advantage of this approach? This allows independent instruction to execute and complete in presence of long latency instructions. So for example, if 1 is like taking 100 cycles and 2 is dependent upon 1, so 2 is waiting in the resting area, but 3 is not dependent on 2 and 1. So it will allow it will allow third instruction, which is independent instruction, to go ahead and execute. So it will not like keep waiting for first instruction to complete. Any questions on this slide? The basic idea is clear to everyone. Those instructions which are like dependent, put them in the resting area, a reservation status, as long as their inputs are not available. When their inputs are available, fire them. And those younger instructions which have no dependencies on the older instructions, allow them to go ahead and execute out of order. So I also need to keep track of the time, right? Okay, so in order versus out of order dispatch. So here is like your understanding how you can compare the two cases, like in order dispatch and out of order dispatch, and we have the same set of instructions, right? So we are showing it for the same set of instructions: in order dispatch, out of order dispatch, right? So, but first you fetch. In the first cycle, you fetch the multiply instruction, then you decode it in second, then it takes 4 cycles to complete. So it is integer multiply, and then you write the results in the reorder buffer, and then you write results back to the register file, right, which is R3. Then in second cycle, you have add is fetched, then it enters the decode, but then it cannot start executing. Why? Because there is a real dependency here, right? There is a real dependency. So it waits until the execution of the I multiply is completed. So that's why it is stalled for 3 cycles. And once the first multiply is completed, then it enters the execute stage, and it takes only single cycle. And after that, then it writes the result in reorder buffer, and then writes the result in the register. Third instruction, it enters the fetch stage, right? But then it cannot go ahead and start execution. Why? Because the decode stage, the instruction, this instruction 2, let me name them: 1, 2, 3, 4, 5. So third instruction cannot enter the decode stage. Why? Because decode stage is occupied by the second instruction, right? So it waits for the second instruction to enter the execute stage, and only then it enters the decode stage, right? So it is also stalled for 3 cycles. And then here, this fourth instruction enters the fetch stage only once the third instruction empties the or leaves the fetch stage. And after that, it enters decode and execute. There is no latency, no dependency, so it can go ahead, but it is integer multiply, so it takes 4 cycles to execute and then enter R stage and W stage. And then in next cycle, we have fifth instruction entering fetch stage, then decode stage. But then again, there is dependency here, between R5 read after write dependency, right? So it is also stalled for 4 cycles, and once the instruction 4 is completed, then it goes ahead and starts executing, because now the R5 is available, and then it enters R stage and W stage. Is everyone clear on this figure? Okay, silence mean everyone is clear, right? I'm continuing then. Out of order dispatch, now how the same set of instruction will be scheduled in case of like out of order dispatch. So first instruction will remain same, right? Second instruction, fetch, decode, but then it is stalled. Why it is stalled? Because there is real dependency here, right? So we can't do the even out of order execution cannot resolve this dependency. So it must wait, right? But the difference is here that we have we allow fetch, we allow the third instruction to be fetched in this cycle, like third cycle, then enter the decode stage, which means that we allow multiple instructions to be decoded at the same time, right? And since it is not using the execute, since it has no dependency on the second instruction, so it can go ahead and it can start executing, right? And then it can write the result in reorder buffer. However, and this is important, however, the order in which each instruction writes the result in register or the memory should be the same as the program order. What does it mean? It means that this is the order of instruction 1, 2, 3, 4, 5. So the order in which they enter the W stage should be same. Like here, 1, 2, 3, 4, and 5. So third instruction, it cannot enter here the W stage. Why? Because it can enter the W stage only after the previous two instructions have entered the W stage, right? So that's why it enters the write back stage, or it writes the result back in the register file only after the instruction 2 has written the result. Okay. Okay, I will take questions. Let me complete first. And then in the next sequence, we are fetching and decoding the instruction number 4. It takes 4 cycles to complete the integer multiply, and then it writes the result in reorder buffer and then in the register file. The last instruction, it enters fetch and decode, and then it must wait here, right? I think there is, sorry for the mistake, but is there a mistake? No. Okay. So then it enters the E stage, execution stage, because there is again dependency here, see, right? And then it enters read stage and the write stage. Okay. Now, if you count the number of cycles, how many cycles are needed to complete the in order execution? So if you count these number of blocks, 1, 2, up to these ones, this one, so you will see these are 16 cycles. It takes 16 cycles. If you do the same counting for the out of order execution, it takes 12 cycles. So out of order execution or out of order dispatch is faster. So definitely we are making here assumptions that uh, all of these stages they take single cycle, and we are keeping everything simple here. So but we are doing the same assumption for both cases, so it's fine. So but what we can see is that out of order execution or out of order dispatch actually gives you performance improvement by completing the same program in 12 cycles as compared to 16 cycles in case of in order dispatch. Now let's have a look at question. Is the performance gain of out of order dispatch worth the extra power and complexity? Yeah, because here this is definitely a toy example, right? So that's why maybe you can say it is not a big gain, like you are improving only by 4 cycles. But in real architectures, the thing is like your uh, the pipeline is deeper, your reorder buffer is bigger, and it allows you to exploit the out of order execution among a larger set of instructions. Here we have only 5. Consider like you have, for example, you have a hardware which allows you to take advantage of out of order execution over a set of 1000 instructions. So it's mean that there will be much larger instructions which you will be able to move ahead of the longer instructions and speed up their execution. As a result, you will see much larger speed up or performance gain. Is it possible to get a situation where all instructions stall? Uh, yeah. So for example, if you have instruction 1, 2, 3, and 4, and there is a dependency chain, like 5 depends on 4, 4 depends on 3, 3 depends on 2, 2 depends on 1, right? So, and when I say dependency chain, it's mean real dependency, read after write dependency. So then what will happen? All of them will be like, each one of them will be stalled on the previous one, right? How can you tell how many cycles and instructions takes to complete? It is actually a feature of the implementation, and like if you you can, it is like feature of the processor. So for example, maybe on one processor the multiplication may take, integer multiplication may take 4 cycles, on another maybe it takes 6 cycles. So it is how it is more about how a multiplication is implemented and pipelined. Okay, so it is not a fixed thing across processors. Let me quickly move to, I have 5 minutes. Okay, so okay, I'm skipping this one because it is more theoretical, and you can like come back to this slide and read it on your own. Uh, but I will go back to the I will move quickly to the the example so that I can demonstrate to you how out of order processes work. So even in out of order processes, two things still remain in order. What are those two things? The front end of the pipeline, which is fetch and decode. So instructions are fetched and decoded in the same order as they are written in the program. And second, the instructions are written, the result of the instructions are written to the register file or to the memory, which is basically the W stage. So this write back or commit is also performed in the same order as the instructions appear in the program, right? Why? Let me not answer that. I mean, if I start to explain why, then it will take time, and maybe it is more for students who are taking a course on computer architecture. I know this is already a lot of architecture here, so let me not discuss that point. You can just keep in mind, like, for example, to handle the situations where interrupts arise or where an exception arise, and you need to handle it. So if you don't do in order commit, then it can create problem. You cannot handle the exceptions or interrupts in the right way or the correct way if the instructions are not committed, if there is no guarantee that will be committed in order. Okay. Okay. No, no, now in between, uh, after the decode stage and before the write stage, are the execution stage. Now the execution, it can be performed out of order. Out of order means younger instructions can go ahead of older instruction if they don't have any dependencies. Okay. And there are like from the output of those functional units. What are functional units? Like, for example, multiplier is a functional unit, adder is a functional unit, right? Load store, the hardware which performs the load and store operations to the memory, is a functional unit, right? So the output of these functional units, they are tags and value, and they are broadcasted to the scheduler. How? We will see an example. If not today, maybe next time. Yeah, that's also true. Wasted power, increased latency. Okay. Uh, so this is known as like hump one, and this is like hump two. Hump two mean like these are the barriers are kind of limitation which you must follow. Okay. I'm also skipping this one. Okay. Hmm. I think it doesn't make sense to start this Thomas Sulu algorithm here, because I will not be able to complete it in any way, right? So let me stop here, and then let me see if there are any questions. What information can travel on the tag and value broadcast bus? Is that like a one-way or two-way communication? This is basically a one-way communication, as you can see from this figure here. So it is one-way communication from the output of the functional units back to the logic which is responsible for scheduling the executions, like responsible for checking that, okay, the which instruction doesn't have any dependencies, and it is younger than the older one, and allow them to execute. So that logic is known as scheduling logic. So these tags move from the output of the function unit to the scheduler. And values, these are so values are the output. Tags and values both are produced by the functional unit. But what is the difference? Value is like, for example, if adder is adding two number 1 and 2, so 3 is the result, so it is the value. Tag is an identifier which I will explain in the next lecture. Okay. I cannot explain it here. Okay. Why does the pipeline go out of order in the middle? To get the benefit, to realize the benefit. Remember, we said, like, if there is a younger instruction uh, which has no dependency on the older instruction, we should allow it to go ahead. No need to wait for the older instruction to complete the execution, and we should allow the younger instruction to complete. So this is like reordering or out of order. So if that's why the pipeline goes out of order, to get the benefit, and not making the younger instruction to wait without any reason. Okay, now I must stop here because we have a student presentation today. Does reordering require intense resources? Uh, very simple answer to this. Yes, very intense resources, because we will see in the upcoming lecture how it works. But here I cannot add, like, in 1 minute or 30 seconds, I cannot answer it. We will see in the next lecture, hopefully. Okay. So let me stop here, and let me.
So it protects the contents of the enclave from other software that's hosted on the same machine by isolating it in its own little section, and that's what they call the enclave. So the enclaves can't interact with each other, and things outside the enclave can't read what's inside the enclave. And it uses software attestation for authentication of the enclave's contents. So whenever you go to sign in, or whenever you go to access your enclave, it's going to check its measurement to make sure that it hasn't been tampered with. And it's also going to use that to identify it. That way it knows which enclave is which and who to allow access to it. So the SGX memory, the enclave uses a part of the DRAM called the processor reserved memory. So the software and peripherals outside of the enclave are not able to access the PRM. The EPC is called the enclave page cache, and it's part of the PRM, and it's used to store the contents of the enclaves. And here's a diagram here. So we have the DRAM, and then as part of that is the PRM, and then a part of the PRM is the EPC, and the EPC has individual enclaves inside of it. So it's multi-layered. So the EPC is partitioned into 4 kilobyte pages so that they can allocate to multiple enclaves on the same machine. So even though you have one machine, you can have several different enclaves inside of it. That way you can host more than one client or service. So enclave page map. The SGX does not trust the system software which needs to allocate EPC pages. The system software is the one that has to decide where the memory is assigned, where the pages go. And so they kind of have to find a way around it. The way they solve it is they use the enclave page map, also called the EPCM. The EPCM checks if the page to be allocated is owned by the correct enclave and whether it was unallocated and a valid type. It helps to enforce enclave isolation. So earlier I said they use software attestation and measurement. This is why it needs to have a measurement. That way it can tell if the page is being allocated to the correct enclave, and it can also make sure that it's being put in the right spot. So this right here is really important to how enclave manages to stay secure. They want to protect against like memory mapping attacks, and the way they do this is they check its attributes to make sure that it's being allocated correctly, that they're not giving the wrong enclave information. So it has right here, it's got valid. So if it's 0, then that means it's unallocated, and you can go ahead and use this space like it's just a free space for them to allocate. It has PT stands for page type, and it's got 8 bits. And this kind of allows you to see what type of information it is. That way, if it's getting something it's not expected, it can just throw an error, an exception. And it's got enclave SECS. And this, we'll talk about this more later, but this identifies the enclave owning the page. That way you know if it's being sent to the right one. So enclave linear address range, also called the L range for short, is used to map the enclave's data inside the enclave. So any data outside of this range is considered untrusted, and it's used to interface with external code. So it's going to need to use some external code every once in a while, but it just knows whether or not it's external based on the address range. So if it's out of here, then it knows not to give it privileges, and it knows not to let it have too much, but it knows that it can interact with it if it needed to. So now we're going to talk about the SCCS again, and that stands for the SGX enclave and control structure. It's kind of hard to pronounce, but anyway, it's used to store metadata about the enclave. So it's used to identify an enclave in the EPCM and by the system software, that we know which one is which. And really important thing about it is that software cannot access the data in the SECS, even like system software. This data is just used for implementing the enclave and for the measurement and software attestation. So some of the enclave attributes that the SECS has are the debug, and this one's really important because it allows you to use debugging features. So if you have this set to true, if you have it in debugging mode, then it loses all of its security guarantees because this allows you to look into the memory, look at its state. You basically is not going to guarantee you any security. So you really need to make sure this is set to off if you're going to implement it in production. And then we have the XFRM, and this just lets you know if the code is being executed. And we have a this bit for 64-bit mode.
Okay, Salib, can you like Salib, can you hear me?
Yes.
Okay. If you have slides on strengths, weaknesses of the paper, or not the paper, the section you studied, and any suggestions for improvement, so you can go to those slides.
Okay. Are we running out of time?
Yeah, we are running out of time. That's why I'm saying
Oh,
you
I'm
can
sorry.
go
Yeah,
to
I'll go
the.
to the. So what this paper has contributed to the field is that it provides an aggregation about information from the SGX. So a lot of those details that I was sharing, some of it was not actually in the official documentation. They wanted to keep some of it hidden because they didn't want people to find certain flaws with it, or they just didn't want to give away secrets. And so they actually had to find some of this information in patents that were required to be published. So they actually have added some to this subject. The paper's conclusion states that there's too much unknown about the SGX to guarantee certain protections, which is what they were hoping to find. And they found that it is vulnerable to cache timing attacks, and they weren't really able to find a definite solution to this. Some strengths that I think this paper had, this section particularly, is despite the lack of information about how to protect it against cache timing attacks, it still provides a lot of information and background about it, and it highlights the fact that there are cache timing attacks that this is vulnerable to, and it kind of shows why. Some weaknesses I thought is the paper is really thorough in explaining how it works, but someone that actually needs to implement this is probably going to have a hard time just going off the paper. And so they're probably going to have to find the original documents anyway that they reference. So if you want to just get a background information, this is good, but this is probably not going to be enough if you're actually going to use this to further some research. My suggestions are, I think it should have more explanations about why certain features are relevant to the security guarantees. That might add to the paper's strength. Also, as Intel continues to iterate on its projects, I think it might be necessary that they do more research to see if there's more information that's been published. And they've probably added a lot of features since it's come out. So I think that this is worth taking another look at. Do we have any questions? Or anything that you want me to explain more? Or... Oh, sorry, I'm trying to get to where I can see the chat. Okay, so it says, so if SGX doesn't trust the operating system, has the EPCM actually stopped the OS from messing with enclave pages? Like, what's the hardware check that enforces that? I'm not sure what the hardware mechanism behind it is, but I know that the the operating system can't access it directly. Like it needs to interface with it indirectly. So it has like a pointer to the enclave security, uh, the the
Okay.
security
Uh,
page, and
uh,
then that's how it finds
Celeb, are you
which enclave.
responding to someone's question? Are you responding to someone's question? I was like,
Yes,
kicked out.
I'm responding to Alvio Frias.
Okay, okay. So, okay, are there any other questions? You can write in the chat box if you have questions. Uh, I have a couple of questions like, for example, you were showing the figure about the memory where there is memory and then there is PRM part of the memory which then contains the EPC, right? Can you go to that slide?
Yes. Yeah. This one.
This one, yeah. Yeah. So in PRM, then other than EPC, what do we have? Is there anything else other than EPC?
Is there something else inside the PRM?
Yes.
I'm not actually sure. So that might be one of the weaknesses of the paper because I don't think they said
So
anything about that.
all of the PRM is used as EPC, or is it like partitioned into chunks and was a part of it is used as EPC and the other parts are used for some other purposes? I don't know. I'm
I
asking you.
imagine that you can probably use other things with it. What I guess is that you can run more than one EPC if you wanted to. Although I'm not sure why you would need to because you can have more than one block here already.
Okay. Any
But
other
they
student, anyone else who want to add to it?
No, I don't think it did a good job of talking about how EPCs are partitioned, like how Caleb said.
Okay. Okay, so I have another question. So, okay, this is question not only to you, it is to everyone. All the questions I'm asking are to everyone, not only to the presenter, right? So anyone who want to respond, feel free. So here in, for example, in this slide is talking about enclave page cache and the paging. So what is your feeling like if we had not covered the background and you didn't know anything about paging and how it works and the address translation? Would your understanding be different of PRM and how EPC is working? Like the level of understanding you have now, would it be the same if you had no understanding about paging and address translation? Basically, what I'm asking is that was it helpful for you to have a background information on paging to in understanding how EPC is working?
I would say that this helps because it kind of like I still am a little shaky on my understanding of paging, but I feel like this definitely helps me understand why it's important, right? So this will prevent secrets from being leaked between the
Okay.
different enclaves here because
If
the
you go to slide number 8, I am here trying to be quick because we also have to fill the class participation form. So here in second row it says page types. So like what are examples of like page types? Are like, for example, can you list two different types of pages which are used in Enclave?
I I know that the SECS is one of the page types. I just kind of assume that it's like different kinds of data that you can access. They don't really go into a lot of detail about, what each one does.
Okay, anyone else who want to add to the answer? Like, if do you know the concrete example of two or three different page types? Like, if they are saying page type, it's mean there is more than one type of pages, right?
Mhm.
Okay. If no, okay, here is the thing. I didn't read this paper, this section like in the past week. I read it like maybe 6 months ago. So things are not very fresh in my mind. So can you go to the next slide then? There was
Sure.
a slide where you were talking about Erlang. Yeah, this one, I guess slide 9, yes.
Mhm.
So enclave linear address range. So who sets this address range? So like I'm assuming that this is a linear address range for, let's say, from 100 to 1000, right? Starting from 100 to 1000. So it is a linear address range and it is virtual address range, right? So
Yes.
who sets this virtual address range? How to read it? L range, right? Who is setting responsible for setting it? Is it operating system
So
or
so let's see here. I think I have in my notes here. I think it's the page information structure.
which is
So
part
that's
of operating system or which is part of something else?
so whenever you're creating the enclave, you have a command called ecreate,
Okay.
and it kind of creates the SECS, and it like puts in some data that needs to instantiate the enclave. I believe in there it actually tells it what the range should be. And let's see here. I think somewhere in here they say what the range is allowed.
So you specify the range as part of create enclave create command.
I believe so.
Anyone who agrees or disagrees with this, again, my memory is not fresh about the paper. I'm just trying to uh, you know increase my information or knowledge. And who handles that create command? Is it operating system? Is it a system call? Are you sending it to the operating system?
Yes, so I think what it was saying is that it's level three software has to be the one to uh,
Okay.
kind of get it started.
Okay.
So
So
the
it is.
the level three software has to make the request
So it is
to
like kind of a switching point, right? Like switching point
yes,
from level 3 to ring 0.
yes,
Okay. Okay.
but
Uh,
I think it has to be a level three to start it.
yeah. Okay. Okay. So then let's stop here and uh, thank you for your
Okay.
presentation. I think it was a nice one. Nice one in the sense that you tried to follow that rubric and tried to like include those components which I mentioned in the rubric. One thing which was like not possible, I guess, is the explanation of the results because you are talking only about some sections. So it's totally understandable if you don't have results. That's fine. Uh, yeah, but I will give one suggestion, like to for the future presenters, uh, have like 5 to 7 slides. The slides, number of slides which are an F to cover in 15 minutes, okay, or at most 10 slides, okay, because otherwise it will not be possible to cover all the material, okay. So and also try to practice it before you actually present it, okay. So having said that, uh, now is the time for your class participation form. Let me give you the code for today. Today is 18, right? So I am sharing the code and I know it's little bit like late. Uh, if you are not done by the time it closes, let me know. Let me extend the its time by 5 minutes so that everyone can. Yeah, you should be able to access it now, but I am going to extend the time by 5 minutes so that you have enough time to complete the form. Yeah, I extended it.